Sound waves are just longitudinal waves that have areas where the air is compressed and areas where the air is rarefied. And the energy just transfers from one place to another. But if you have two sources of sound, like two speakers playing their individual sounds in unison, if those sound waves overlap, like they do in this area here, you could get it so that the sound cancels. Because if these two waves moving back and forth in unison are offset by a half of a wavelength, then the compression from one wave will fill in the rarefaction of another wave. And what we're doing is we're just mixing high pressure air with low pressure air to just get average pressure air. So there'd be no changes in the pressure. And this is a neat little device that demonstrates that. On this side we have a little buzzer that just makes this a very annoying tone. And these PVC pipe here is going to split the sound. Some of it's going to come this way, some of it's going to go that way. And because the distance along the top is the same as the distance along the bottom, those two sound waves are going to meet up in unison and come back in unison. So let's say the blue is a crest and the blue is a compression and the light blue is a rarefaction. You ended up getting rarefaction on rarefaction and compression on compression. It will just be that sound meeting up again. But going from here to here is a whole wave, and just one complete compression would just be half a wave. But this device here can stretch out like a trombone. So if this distance here is a quarter of a wavelength of sound, and this would also be a quarter wavelength of sound, the sound that traveled this distance traveled a quarter and another quarter. It traveled half of a wavelength farther. So it starts out in unison, and as one wave goes over the top and one wave goes over the bottom, when they meet up, because the wave that traveled the top traveled half a wavelength farther, it arrives half a wavelength behind. So you're ending up with compression on rarefaction, and then a moment later it'd be rarefaction on compression, but it would cancel the sound. You put your ear up to that and you would not hear any sound coming out of that hole. Put your ear up to here and it would be painful, it'd be so loud. Now it doesn't have to be just a quarter of a wavelength. If we extended that up farther to 3/4 of a wavelength, because if the sound travels this way 3/4 and comes back and travels another 3/4 longer, that's 1.5 wavelengths farther. So the distance of this distance 1 here is going to be distance 2 plus 1.5 wavelengths. That extra half wavelength makes it so the sound aligns half a wavelength behind, and it would cancel. Now, instead of confining these waves to tubes, let's just let the speakers make sound in a room. And we're just going to show it as a series of concentric circles here. A little flash warning: if you have epilepsy, this might trigger this, so maybe bypass this part. Here we go. So these waves are making compressions and rarefactions, and the dark areas I'll say are compressions, the light areas are rarefactions, and if you have just one speaker, that's what it's going to look like. But if you have two speakers and the second speaker is doing the exact same thing as the first one, the waves of one will interfere with the waves of the other, and you get this pattern. You'll get these dark blotches here that are compressions on compressions, and you get these light areas that are rarefactions on rarefactions. And compression on compression is a really big compression. Rarefaction on rarefaction is a really big rarefaction. But you also get these areas where a compression falls on top of a rarefaction and the sound will cancel. So let me just zoom in on those areas here. If you put your ear right here and listen, you're going to get really big compressions and really big rarefactions. Put your ear right there with the two speakers playing, it's going to be a really loud sound. But if you put your ear over here, there aren't that really big changes in pressure. It's just this kind of this constant So the sound would cancel out there. You wouldn't hear any sound when two speakers are playing. But over here off to the side, you do hear two speakers again playing because you have the same situation as you did there. Now, if those speakers were not there, but if they moved apart a little bit, we'll get a similar interference pattern, but where they interfere will be in a little bit different places. So we're going to get a lot more of them. And if we zoom in on just those ideas here, right here you hear a really loud sound, compression, rarefaction. Next to it you wouldn't hear anything. Here you got those really loud sounds, and next to it all canceled out, loud and canceled out again. So I want to acknowledge that we're going to take this a little further, but not in this video. When we start talking about diffraction of light, I'll readdress and we'll develop an equation that relates how far those two sources are away from each other, the wavelength of the sound or light being emitted, how far we are from where we're listening, or like if there's a screen there, and how far the different dark areas or loud sounds would be here and out there again, and the angle that it makes. I'm not going to do that in this video, but we will revisit that when we talk about diffraction of light. So I need you to experience this. So I have these two speakers set up, I have a tone generator, and these are making the exact same tone. The speakers are moving back and forth in perfect unison. And I'm going to play the sound here, and we're going to listen, and this is the graph of the actual sound from that video. So listen. And we do get these areas where it was totally canceled out, but I was moving, so it only was canceled for a moment, and areas that are really loud. But one thing about this is I was expecting there to be almost complete cancellation like there was here, and cancellation should be here, just like we had in those places. I didn't get that, and I was a little surprised. And what we do in science is we make observations, we don't fudge our data, but we try to understand what we're seeing. So when I did not get full cancellation here and here, I'm trying to think, what is going on? Well, if they had canceled out more there, I think it had to do with if this distance going from the speaker to the microphone was half a wavelength farther than the distance from this one to here, it would have canceled out completely. And there's going to be some angle where that happens. I think what happened was it was my function generator here had a large flat surface on it, and I was getting an echo off of that. So if those two were half a wavelength difference, they would cancel out completely and no sound would have resulted. But the echo I was getting off of that made it so that it didn't cancel altogether. And then by the time I got around to this other side, the angle was off, so it wasn't reflecting back in the microphone to cancel out completely there. All right, noise cancellation. Noise is characterized by very sharp, irregular, jagged waveforms, and it's very unpleasant to listen to. So we can get noise canceling headphones. And so if this is the sound that's coming into my ear, I can get rid of that sound if I play that exact same sound, just as loud and exactly the same, except it's flipped. When one sound was arriving at a, say, compression, we're making an equally loud sound, but as a rarefaction. And when those two sounds interfere, there's going to be no net sound. You're going to cancel out that noise altogether. So if this is the headphones, there's a little microphone in there that's listening for sounds that are coming from the environment. And it listens for that and it plays back that exact same sound, the exact same waveform, but flipped. So this green wave is being blasted into your ear just as loud as that sound is, but the resultant of those two cancel each other out and you don't hear any sound. And if you've played with noise canceling, they're pretty darn good, but there is maybe still some room for improvement in creating the exact same waveform. Now let's say you're listening to your noise canceling headphones and maybe you're flying an airplane where you don't want the noise of the engine, but you still want to be able to either listen to music or maybe more importantly, talk to the air traffic control. So you want to be able to cancel all that extra noise of the engines and air and rushing and stuff, but you still want to be able to hear the waveform of air traffic control, or in my example here, I'm talking about music. So instead of blasting this green, we'll call it anti-noise wave, we want to blast that wave and the wave from music. Well, you would need two speakers to do that, or you just blast the resultant of those two. The blue wave, which is our music, and the green wave, which is our anti-noise, you blast the resultant of those two. And it's going to be kind of going up and down like that blue wave, but also have that jagged form like our anti-noise. And the red is what's coming in from the environment. The speaker in the headphone is blasting this cyan colored wave. And when both of those waves arrive at your ear at the same moment, the resultant is just this original sound music wave that we wanted to listen to. It's pretty cool. All right, now there's kind of a new topic we want to talk about. It's still with interference of sound, but it has to do with what is called beats. And beats occur when two notes that are not the same. My other example, I was playing the same notes and just had them in a little bit different positions. But if we play two notes that are nearly the same, but not the same, we get a weird phenomenon called beats. So let's say this represents 1 second of time, and I'm playing 20 hertz with one sound and 21 hertz from the other sound. I should acknowledge that 20 hertz and 21 hertz is right at the lowest frequency we can hear, so some people might not be able to actually hear that, but I didn't want to do 1,000 hertz because I'd have 1,000 waves there. But if you count, there would be exactly 21 complete red waves and only 20 complete blue waves in that 1 second. The red had a little higher frequency, so it had a little shorter wavelength. The red and blue started out together, but the red had a little shorter wavelength, so after one complete cycle, the red has fallen behind the blue a little bit. After another complete cycle, the red has fallen a little further behind, and the red falls farther behind the blue, and farther behind the blue, and farther and farther and farther. Until right in here, about midway, the red has fallen an entire half wavelength behind the blue wave. You'll get a compression of the red lining up with a rarefaction of the blue, and it will cancel the sound out there. We got crest on crest, or compression on compression, and this is the resultant wave of those two waves playing at the same time. A little different frequencies. You're going to get a loud tone, and then it's going to get soft for a moment, and then it's going to go back to loud. You will get one beat. Going from loud to soft, back to loud is one complete loud, soft cycle in that 1 second of time. So that going from loud to soft, back to a loud was one beat per second, or we say the beat frequency was 1 hertz. And just notice this. Notice that it was 1 hertz in beat frequency, but these were different by a frequency of 1 hertz. Just subtract them to find the difference is how you find the beat frequency. So let me just demonstrate that. Remember, I can move these masses here and adjust them up or down to change the frequency of this fork. This one doesn't change, but if I play them at the same time, we hear that pulsing of loud and soft sounds. About 1 loud and soft every second. Let's do that again, but with 20 hertz and 22 hertz. The same frequency as before, but a little higher frequency here. So because this was 21 before and now it's 22, a little higher frequency is going to have an even shorter wavelength. So they started out red and blue in unison. After one cycle, the red has fallen a little further behind than it did in my last example, and then a little further behind, a little further behind. By the time it gets about right here, it's half of a wavelength behind, and it falls further and further and further and further behind. Right here in the middle, it's fallen an entire wavelength behind, but it puts us back to crest on crest or compression on compression. And the resultant waveform, where it was crest on crest, you get a really loud crest. Where it was crest on trough, cancels it out. Loud, so it goes from loud to soft to loud to soft, back to loud. That is 2 complete loud, soft, loud, loud, soft, loud cycles in 1 second. We heard 2 beats per second. The beat frequency was 2 hertz. And again, notice that it was just the subtraction or the difference of the 2 frequencies. So we'll play that here. I have adjusted this so that they're a little further off. And listen to those 2 tones. It's beating loud, soft at a faster rate, about 2 beats per second. All right, we'll skip ahead to 20 and 24 hertz. So they're starting to get a significant difference in frequency. So they're getting a significant difference in wavelength. So after they start out in unison, and after one complete cycle, red has fallen behind, and then even after just a few cycles, it is an entire half wavelength behind. And it's falling, the red is falling further and further behind. Here the red is a whole wavelength behind the blue, and it's back to in crest on crest. 1.5 wavelengths behind, 2 wavelengths behind, 2.5 wavelengths behind, 3, 3.5, and by the time it gets back to here, it's 4 full wavelengths behind, because there were 4 full waves that were different in that 1 second. The resultant waveform would have loud, soft, loud, soft, loud, soft, loud, soft, loud. You would get 4 complete loud, soft cycles in 1 second. The beat frequency would be 4 hertz. Difference by 4 hertz. So I'll play that. And these are really pulsing fast. Maybe about 4 waves every second. Now I've adjusted these so they have almost identical frequencies. If this is 261 hertz, this would be right at 261 hertz. So when I play those, it's just this nice solid tone. There might be a long pulsing of loud and then soft, but it's going to be pretty darn close to the same note, so no beat frequency. All right, just a couple of things to be careful of is that if I play this note at 261.6 hertz, okay, that's the frequency of the fork, and I'm trying to tune the piano. So I play middle C here, and it's not playing the right frequency. We have to tune it and adjust the tension in the strings to make it play the same. But if I play this frequency and this note at the same time, and I count and I hear 2 loud softs every second, I know that this note and this note differ by 2 hertz. The thing we have to be careful is that we don't know if this note here was 2 hertz higher than this note or 2 hertz lower. It could be either. If it was 259.6 or 263.6, both of those numbers differ by 2 hertz, and it would sound the same, or the beat frequency would be the same. So we would not be able to narrow it down which of those 2 it was unless we went a little farther. So let's say we tightened the string on the piano just slightly, and we know that when we tighten it, the frequency goes up. So if the frequency went up slightly and now we hear 3 hertz, what is the frequency of the string now? Well, if I tighten the string and this frequency went up slightly, or if it was this one and it went up slightly, we can now answer our question because it must be this frequency, because when we tightened it slightly and it went up to 3 hertz, we know that this differs by the 3 hertz that we were hearing when those two notes were played together. So just be careful. You can't know whether it's higher or lower, just that it differs by 2, unless you had some more information. And let's say that these two musicians are tuning their violins, and one sound coming off of that is 0.784 meters in wavelength, and the other is 0.777 meters in wavelength. If those two sounds are played together, what would be the beat frequency that we hear? Well, you'd be tempted to subtract those two and get 0.007 meters in wavelength, but we have to be careful. To find the beat frequency, it's the difference in the frequencies, not the difference in the wavelengths. Okay, so I would have to find out what the frequency of these wavelengths are. I would have to know the velocity of sound. So if it's 345 meters per second, I know the velocity, I know the wavelength, I can rearrange that equation and solve for the frequency. Velocity divided by wavelength, that's the frequency of this note, and that's A, 440 hertz. This is this velocity divided by this wavelength. This was 444 hertz. So if these played together, now we can subtract and know that they would pulse at 4 beats per second. Okay, one last example, and this is a pretty cool one, is that in the program Audacity, you can generate a tone and pick what tone you're going to generate. So I picked a tone of 20,000 hertz. I picked another tone of 19,000 hertz, and then just a tone of 1,000 hertz. So 20,000 hertz, really, boy, unless you're a little kid like 2, 3, 4 years old, you might be able to hear that tone. But the older you get, the less high frequencies you can hear. And I think even as a teenager or a young adult, you might have a hard time even hearing that tone. I can only hear about 16,000 hertz. That's my threshold of hearing. So if I play those two tones, or if I play that tone, I shouldn't be able to hear it. If I play that tone, I shouldn't be able to hear it, and I can't. But if I play the two together, they will beat at a frequency of 1,000 hertz. So they differ by 1,000. So let me do that here. I'm going to unmute that, and now I'm playing that tone. You can see it's loudly going there, but I can't hear it. Let me unmute the other one. And again, we see that it's loudly playing, but we can't hear it. Let me play them together now. Now we hear it, because they're beating together at 1,000 hertz. And it sounds the same as just if I had played 1,000 hertz there. So anyway, that's a little bit about interference of sound and how you can cancel sound, and then what beats are when you play two frequencies that are very similar. Hope you enjoyed and hope you learned a little something today.